Welcome back, students. Let us now begin section 2, related rates. What did we discuss previously in section 1? We went through the theory of implicit differentiation. We went through some examples as well, but those are a bit hard, so I marked those as optional videos. In other words, many students must have went through the implicit differentiation theory and then coming directly. So some further review is in order, I guess. So what is implicit differentiation? We begin with a relation between x and y. Of course, I could have selected other characters if I wanted. Okay, one relation, and then we get the second relation by taking the derivatives implicitly. You can do it either this way, using French notation, primes, or like that, using German notation, dx dt or dy dt. In any case, remember this. Whenever you apply the derivative rule to x, x prime pops up. Whenever you apply the derivative rule to y, you get y prime. And of course, you can use dx dt and dy dt respectively, if you prefer. In any case, here's one relation, the relations between x and y, and here's a second relation, the relations between not just x and y, but also x prime and y prime, the derivatives. The rate of changes are related to each other. That's the key here. You see? Related rates. Okay, let's go ahead with an example problem. And here's the first example. If a snowball melts so that its surface area decreases at a rate of 1 square centimeters per minute, find the rate at which the radius decreases when the radius is 5 centimeters. Okay, at first glance it looks even more intimidating because we don't have any formulation. You have to somehow cough it up. But then again, it's not too bad because it's coming from geometry. So what's the relationship between the surface area and the radius? Remember? Well, there you go. From elementary geometry, surface area and the radius, S is 4 pi r squared. So we have one relation, and let's get the second relation by implicit differentiation. Not too bad. Let's take the derivative implicitly. S prime is equal to 4 pi. And then what's the derivative of r squared? 2r, but r prime pops up. Maybe we can simplify this a little bit further. 2 times 4 is still 8 pi r prime. All good? Or if you prefer German notation, you can write like this. dx dt and then dr dt. Sorry about the typo. Okay, which do you prefer? In my solution here, I use French notation. So here, let's use German notation to answer the question. First equation here, second equation there. First equation is the relationship between the original variables, S and R. The second equation is the relation between not just original variables, but also the rates. The rates are related like this. Okay, we have 4 known variables and only 2 equations. We have a problem. But then again, something is equal to 1, something is equal to 5. The problem gave you 2 of them. Out of 4 knowns, SR ds dt and dr dt, yes, they are 4 known variables. This problem gave you 2 of them. So we're going to be down to only 2 unknown variables with 2 equations. Or we can do it. But here's a big problem. Which is which? What is equal to 1 and what is equal to 5? There goes your first challenge. Stop the playback and try to get it done by yourself. Got something? Okay, alright, I did some preparation. Now let's plug in some numbers. What is equal to 1? Surface area. Do I plug in 1 right here? No, not really. It says it decreases at the rate of. So the surface area is not equal to 1. It decreases at the rate of 1. So I put this 1 in wrong place. Not in place of s, but in place of ds dt, the rate of change. So that should be equal to 1. Remember this color coding. Now what is 5? Radius is 5 or rate of change? It says radius is 5. So r is 5. So this one and that one. And that's where I'm going to plug in 5. Oops. Okay. First, I just plug in r equals to 5. Second, I just plug in r equals to 5. And what we want to find the rate of change of the radius. So rate of change of the radius, what is it? It's a derivative, it's dr dt, and that's a quantity I have to find out. See the structure of the problem? Let's go back. Original problem is just geometry, so from there you can get s equal to 4 pi r squared. And then you can take the derivative implicitly to get the second equation like this. Assuming that you got the formula, taking a derivative implicitly is not difficult. Now, hard part begins. Plug in the numbers in right place. Something is equal to 1, something is equal to 5, but which surface area decreases at the rate of 1 square centimeters per minute. So it's not s, but ds dt is 1. So as it did the color coding here, we get this left-hand side blue. And radius is 5, so plug in r equals to 5. The red is 5, so as you have this color coding. And the quantity I'm looking for is the rate of change of the radius. So what do we have? We have 2 equations, which I'm highlighting in bold here, and 2 unknown variables, s and dr dt. 2 equations and 2 unknown variables. Can I solve it? Actually, yes. As a matter of fact, this is really easy because s and dr dt are not intertwined here. You can get s from here, and you can get dr dt from there directly. It's actually pretty simple. As a matter of fact, it's so easy that I'm more compelled to complete it right here. 1 over 8 pi times 5, so 40 pi. And that's approximately equal to, well, about this 0.0079. I'll say this is about 0.008. Okay, there goes the full solution. Okay, I take it back. It's not a full solution. Just the computation part of it, just the formulation part. For the full solution, let's open this up. You see, all these explanations here, what steps we are doing, those parts should be included as well in order to become a qualified full solution. From the surface area formula of a sphere, we get S equal to 4 pi r squared. And the second equation we get from the implicit differentiation. So here we see how the surface area S and the radius R are related to each other. And here from the second equation, how those rates are related, S prime and R prime. Previously I used German notation. Here I'm using French notation. So we have 2 equations and 4 unknown variables. It's not good, so we have to plug in some numbers. It turns out S prime is, well, I'm using not just 1 but -1 to be a little bit more strict because it's decreasing. Okay, all right. And R is equal to 5. Plug those in and then do your computation. The problem did not ask you this S value, but I could have found out. Just plug in R equals to 5 to this equation and run your computation, about 315 square centimeters. And then as for dr dt or R prime, 1 over 40 pi, negative 0.008, or decreasing in 0.008 centimeters per minute. Here, you don't really have to worry about pluses and minuses. Everybody can understand it's decreasing. And I use all the units here, but if you're not comfortable with all those units, then you can just skip all those units. So never mind about all those units. Okay, here it can get rather confusing. Okay, does it look better? Okay, that completes the problem. Remember, from geometry you can get the first equation. The equation gives you the relationship between the original variables, and the implicit differentiation gives you the relation between the rates. 4 unknown variables and only 2 equations, so you have to get 2 of those values from the problem and plug those in, then you get a well-posed system of equations. You can solve those.